So let's look at Bernoulli's equation. We are proving that with the help of work energy theorem. So let me use this example so that this makes more sense and the transition becomes easy. So what I'm talking about is throwing a ball up in the air, say on the surface of the moon, right? So this is the top and this is a journey. It goes up and down. So what is the relationship between kinetic energy and potential energy as and when it moves? Will the kinetic energy and potential energy remain the same throughout? No, right? Individually, they don't. So kinetic energy value will not be the same at the top in comparison to the kinetic energy and potential energy at any other point. But the total is constant. And this keeps changing. This also changes. Do you guys agree? Do you remember all this? Similar to this. Okay, extending this idea, we have ideal fluid moving through a pipe. So here your gravitational force is acting on it, and there is change in height. And with all of this, you have this particular changes happening, but of course there's one thing that is remaining constant. When we talk about Bernoulli's equation, what we are dealing with is, we are dealing with an ideal fluid, which is seeing a steady streamline flow through a pipe which is varying in size and height and everything. Okay, guys. So what happens to the energy? Is there an energy form change? Do we see like here, how we saw the kinetic energy and potential energy, the energy, it increases and decreases, right? Similar to this, is there an energy form change that we see over here? Relating that is your Bernoulli's equation, and we are proving this with work energy theorem. To put it in simple words, say our system is made up of all the particles starting from point 1 to point 2. Okay, so this is when you started observing, and this is after some time t. So you can see that the bunch of particles is moving to the right. So this is 1 to 2, 1 to 2. So this bunch of particles has moved to the right. So it is flowing to the right. Okay, guys. So when this happens, what we are trying to see is what happens to the energy. Will the energy, the different mechanical energy that we get to see, will it remain the same? Will it change? That's what we are trying to understand. Okay, that's the agenda. So to do this, we are considering a stream tube of fluid flowing from 1 to 2 in a pipe of varying cross section and height. So we have different cross section and height. So let me kind of streamline this a bit. So we have a pipe whose area of cross section over here is A1 and this is A2. So this is when we have at 0 second, and this is after some time t, delta t. Okay, and now we have to also consider that this is steady and streamline flow, and all of this is incompressible fluid with density of rho. It's non-viscous, so there's no friction, there's no loss of energy in that form, and there's no other form of energy being lost, right? Energy is not lost in any other form. Okay, so first thing that you need to observe over here is, understand over here is, this system is exposed to two different forces. Since this is fluid, right? You know that fluid will exert pressure. And let's call this as P1. And here also it will exert pressure. Let's call it as P2. Do you guys agree? There's a continuing force acting over here. And of course, to oppose the motion over here too, because the fluid behaves that way. Remember, right? So if I keep any surface inside a fluid, it will exert pressure in all the direction. So using that fact, can you see that this is experiencing pressure in all the direction? The system of particles is experiencing pressure at both ends. Quite simple, right? Because of the other set of particles which makes up the remaining of the fluid, the surrounding per se. So if this is my system, I'll just write it lightly. If this makes up my system, this would be my surrounding. This, and of course here too is my surrounding. So my surrounding on the left is pushing it forward. That's why it's moving forward. Surrounding on the right is also pushing it, but it's pushing it back. Okay, till now everything is clear. Post this, it's very simple. Till now whatever I said, it has to be clear. You have a bunch of particles that is connected to a tank, and the tank is pushing it forward. So it moved forward. Right? And the area of cross section is A1 and A2. And the pressure that the system experiences at one end is P1 and the other end is P2. So because of which the system has moved forward. It has gained some energy. There is change in energy. Okay, so let's start by this. We don't need. This is for you guys to understand that how you got an expression over here and you ended up with few numericals and derivations and everything. Similarly, we are doing things over here as well. Okay, guys. So let's start with looking at the moving fluid. Okay, so we are considering the time frame delta t. We have the left end and the right end. The left end of the fluid segment moves forward by, let's call it as delta x1. Okay, so you can see that the particle was over here, bunch of particles, and it has moved to this point. Sorry, let me change the color. So from here to here, and this value I'm calling it as delta x1. Actually, you have to use the same diagram. For your understanding, I'm just drawn two diagram. I'll finalize it. So this movement is delta x1. Okay. Again, see guys, how we saw the ball moving up and down. Similarly, this is just set of particles that is moving. Then at the right end, we have right end. What do we have? It moves, the system moves, the particle moves by delta x2. So delta x1 and delta x2, will they be same? So it was here and it went to this point. So this is delta x2. Okay guys, will they be same? Oh yeah, sorry, let me come back to this. Is delta x1 same as delta x2? No, right? Why is that I have drawn it different? Why is delta x1 not equal to delta x2? The volumes entering and leaving must be equal. Why? Because the fluid is incompressible, and with the help of, when we have an incompressible fluid, and with the help of the continuity concept that we saw, the volume has to be fixed. Basically, it's common sense. If you have to make space for 10 people and if the place is packed, all the chairs are occupied, if you have 10 more people coming in, 10 people have to go out, right? That's your continuity. So the shaded volume, I'll be changing the diagram actually. At the left end equals, that's equals actually, the shaded volume at the right. So V is volume, by the way. A1 delta x1 is equal to A2 delta x2, and yeah. So basically what I meant is, let's finalize this itself. Okay, so this is the left volume and this is the right volume. So you can finalize this as the diagram. Okay, so this is your area of cross section A1 delta x1. This volume has to be equal to this volume basically. Okay, it has to be so. There's no other option. Agree? Now, so with this understanding, so let's start with as per work energy theorem. What we're looking at is work done by any external source will change in the mechanical energy of the system. This is a possibility. And when we discuss about change in mechanical energy, we're looking at change in the kinetic energy plus potential energy. So this is nothing but kinetic energy at 2 plus U minus the kinetic energy 1 plus potential energy 1. Okay, so 1 is over here, by the way. So this is 1 for us. I should finalize this, right? And this is 2. Let me write 2 over there. It's not visible. And this is 1. And this is 2. Okay, so why is that I'm talking only about this section? Why not in between? So in between, you can see that nothing has changed. In between, we already had this section of fluid before and after. So those set of those values will cancel each other. So we don't have to discuss that. Again, I repeat, in between region is from here to here. This, which is part of the system, is not going through any changes. Agree? They're not going through any changes. So we are ignoring that. So the change in the system's energy is to do with part 1 and part 2, the difference between them. This is the only possibility. Okay. So in between, what is happening? In between fluid, the system, let's write the reason as well. The system in between 1 and 2 does not see any change in its energy. So we can ignore that. Actually, it's a very simple derivation. Just that I am explaining it a lot. Okay, guys. Now, so let's take one by one. So we have LHS. That is work by external force. So here the work is done by the surrounding, of course, external sources by the fluid on the left and the right. So the left is pushing it forward, the right is pushing it back actually. So we are going to make use of using work is equal to force into displacement. So at point 1, what we have is work 1. Force is in the form of pressure into area and displacement is delta x1. Agree? But this is nothing but your volume V, right? We already discussed that. That's why it helps. Okay, it's here. So this is 1. So this is from 1. Now at point 2, we have P2 into A2. This is force. This is your displacement. While this makes up your volume. And so we have V again. So this is your LHS, while my RHS will be half m V square 2 plus m G H2. Okay, this I have not described. Let us talk about it now. See, if I take up any particle over here, it will have a certain velocity, right? It's moving, so it will have velocity. That I'm calling it as V1. And particles at this part will have velocity, and that velocity I'm calling it as V2. Okay, so we're actually finalizing this, right? So where do I write it though? Don't have space. So V1, V2. Not exactly an ideal thing, but because I also have to show you guys the height. So guys, you also have to do a bit of jugaad. So it has gained potential energy as well, right? On an average, this has been your height. Okay. So this will average out to this point, and all of this will average out to this point. That's why I marked in the middle. So you can see I'm marked in the middle. I could have taken a better color combination. And so we have these values, right? They are moving with a velocity, certain velocity, and written that. That's it. Minus half m v1 square plus m into g into h1. Now, so mass is equal to density into volume. So on substituting that, what we have is half rho v. Actually, you know what? Let's not waste a lot of writing. Therefore, okay, ext is equal to change in the kinetic energy plus potential energy will be equal to, so we have P2 into V minus P1 into V. Okay, sorry, my bad. Oh yeah, one thing I missed out. My bad. Let me correct that. One small thing, my displacement, my pressure is in opposite direction to that of the force, guys. Movement, guys. So here I have to consider negative. So reason being, the force and displacement are in opposite direction. So let me explain this. See, the particles are moving to the right. The pressure is pointing to the left. So work done by this pressure will be negative. That's all I meant. So that's why this is negative. So the work done by external force will be what? W1 plus W2. And on the RHS, I'll just keep this as it is. So now on substituting, so what do we have? W1 is P1V and W2 is minus P2V. And on the RHS, we have half mass, I'll write it as rho V into V square. So please understand that this is volume and this velocity. This is supposed to be small. This is big. Right, and we have plus m GH2 minus half rho V P1 square minus rho V GH1. So all in all, what is common? Your volume is common. Is that correct? Exactly. And bit of rearrangement. P1 is positive over here while all of this is negative. So I'll shift all this once to the left, and P2 I'll shift it to the right. And so you can see that the pressure, the kinetic energy and the potential energy for a ideal fluid flowing through a pipe, okay, single pipe in a streamlined manner, the pressure, the kinetic energy and the potential energy will remain constant. Okay, will remain constant. That's the whole funda over here, and that's your proof. So you guys can ignore this diagram. So you can, I think nothing else has been missed. So you can just make use of that. Yeah, I think now it's okay. Again, it's actually, let me revise it off once. So a bunch of particles is making up our system. The particles are moving from left to right. So there is change in shape and height and everything. So we are covering up all the possible scenarios. This movement happens because there is a pressure difference. If not, then the fluid will not flow. So in our case, in this particular case, there is change in potential energy, there is change in kinetic energy. And this change has occurred because of the pressure difference. So the work is done by the pressure. And we are equating, it's a simple expression. The external work will result in change in the mechanical energy of the system. So based on this very fact, we are deriving it. And this is a very simple expression, this you know of. And the work is nothing but force into displacement. And kinetic energy and potential energy is half mv squared, then mgh and all of that. Substitute it, simplify it, and you get the answer. Very simple thing. But yeah, I took time to explain why this happens because I've seen many kids, they don't understand exactly what is happening. Actually, I planned for almost 2 hours to come to this point, as in how to tell, what to tell, especially the starting part. Everything else is quite simple. Okay, guys. So it took some bit of planning. I hope I was able to deliver. Now it's time for you guys to pause, have a look, learn properly.